Hello students, this video is on tangent properties. I promise it will not be 13 minutes. Just to remind you, if I draw anything with red, that means that I'm referring to the hypothesis, and if I do anything in blue, then I'm referring to the conclusion, or the then part. Okay, or the then part. All right, one little reminder, a tangent touches a figure at exactly one point. So if we have a picture of a happy face, the tangent line would be the line that touches the happy face at one point. Okay, so touches happy face at one point. If it touches the happy face at 2 points, then we call it a secant. But these conjectures are all about tangent lines to a circle. The first conjecture that we have is called the tangent conjecture, which says a tangent to the circle is perpendicular to the radius drawn to the point of tangency. So let me draw a picture because that wording can be a little confusing. So the if part would be if we're drawing a tangent line to the circle. So if, that's pretty good, we draw a tangent line to the circle, then the radius drawn to that point right there, that point of tangency, the radius will be perpendicular. So let me draw that right angle marker to show that it's perpendicular. Right, so that's all the tangent conjecture says. That's true for any tangent that we could draw on the circle. Right, so take a second to copy that down into your video guide. All right, the other conjecture we have is called the tangent segments conjecture, and that says that tangent segments to a circle from a point outside the circle are congruent. This doesn't really fit into if-then form very well. The one thing I can do for the hypothesis is let's just start with some point outside of the circle. Right? If I draw a tangent line that connects this point to the circle, it will connect in two places. So I can draw two tangent lines through this red point here. So I'm going to actually use the line tool. That way I don't totally botch this up. But I can draw a line through the point, touching the circle at exactly one point. And that's pretty close. All right, I can draw another line right? So those are my two lines. This segment, I'll do this in blue. This segment from the point of tangency to the point is congruent to this segment from the point of tangency to the point. Right? So it's kind of like we're drawing a dunce cap on the circle. Both of those sides must be congruent. That's what the tangent segments conjecture is. Right? Those are the only two conjectures that we have for this section. I am going to share with you two definitions, then we'll practice some of these problems together. So the two definitions I have are, there are two ways for circles to be tangent with each other. We could have circles that are internally tangent. That would just mean that there's a circle that's tangent to the line, then there's another circle tangent that's inside that other circle. And these drawings are atrocious. I apologize. It's just getting worse. I'm going to stop going over it. So that would be if they were internally tangent. If they were externally tangent, then the circles would not be inside each other. So there would be a circle here that's tangent, and then a circle here that's tangent. So that's just a subtle difference. Sorry about these awful pictures. Okay, let's look at an example together. So follow along with this example in your video guide. We have a circle with rays M and N drawn, and we're told that they're tangent. we're trying to find the angle measure of W. Right? So what information could we add to this picture to help us find the measure of W? We can use the tangent conjecture to say that these angles are 90 degrees. Right? So now we have 90 degrees, 130 degrees, 90 degrees. Think about how would we find W? Try to do that yourself. So pause the video. Okay, hopefully you tried this before you're looking at the answer, but we could use the polygon sum conjecture, which would say 130 degrees plus 90 degrees plus 90 degrees plus W equals 360 degrees. Right. So that is going to give us a value of 50 degrees for W. Right. And for the application problem, pause the video to read this problem to yourself. I want you to try this drawing, and then once you've tried, check out my solution. And I hope you paused first, but here's my solution. So if Pam is swinging the ball in a perfect circle, we know that the motion is going to be circular. Okay, so she's swinging it around and around and around. Eventually, she's going to let it go, and I'm going to say she lets it go right. These drawings are atrocious. I'm going to say she lets it go right here. Okay. If she let it go, it would continue in a straight line. All right. So that's the overhead view of the circular path. The ball's straight path toward the target area, which I guess will be right here. Okay. And how is her arm going to be positioned when she's letting go of this? If you're spinning something around, your arm is going to be straight out. All right, so in red, I'll draw her arm. So here's her head, and her arm has to be perpendicular to the path of the hammer that she's throwing. All right, so as promised, under 8 minutes. That's it. If you have any questions, make sure to write them on your video guide or bug me in class about it. All right, thanks guys.